Okay, so day 2, we are going to begin our talks about extrema. And today we're actually only going to talk about absolute extrema. We are going to eventually, later on down the line, talk about relative extrema as well. But for right now, we're just talking about absolute extrema. And a definition, a formal mathematical definition, is what I have up here on your screen right now. Let f be defined on an interval containing a point c. F of c is the minimum. Notice that the y value is the minimum. X would be where it happens. But f of c is the minimum of f on the interval if f of c is smaller or equal to, it can be equal to, but smaller than every other value for every other y value in your interval. Then you are the absolute min. So logical standpoint of that, let's just kind of use a parabola. Here would be f of c. If it is smaller or lower on your y-axis than every other point in the interval, then that is considered an absolute min. If f of c is considered the maximum if f of c is greater than or equal to every other value in the interval. So these are called your absolute extremas. They can happen a couple different ways. So I just gave you a parabola. In that example that I have up there in green, the graph has an absolute minimum, but it does not have an absolute maximum because those arrows are going up forever. You can have a parabola goes upside down now, that this one would have an absolute max and no absolute min. Because absolute means it is for sure, for certain, the highest or the lowest value over the entire domain. Now, there's this theorem called the extreme value theorem. If f is continuous on a closed interval, and that's your key, it must be on a closed interval, then f has both a maximum and a minimum on the interval. So the last example that I gave was a parabola where we have an absolute min, but we have no absolute max. But this is on an open interval. If we were to close that and deal with an interval of some sort from, let's say, A to B, you are then guaranteed to have at least a max because I have a stopping point somewhere. So if you think about where absolute maxes can occur, they can occur either on the endpoint or at any critical number that you have in the interval, if the critical number falls in the interval. So if we just had, you know, a line that doesn't go up or doesn't come back around, you can have an absolute max, an absolute min, or you could have where you're going to have a critical number and then that comes back up. The two endpoints do not even need to be at the same height, but here, if I'm looking at this graph, the absolute max comes from an endpoint where the absolute min comes from what we have as a critical number, which is why we needed to learn how to solve them the other day. So our goal for today, we're going to talk about relative minimum and maximum later on after your first quiz. But your goal for today is actually finding absolute extrema on a closed interval. And to do so, we have to understand that your absolute extrema could happen at either an endpoint or at a critical number. So the first thing that we have to do, we obviously know the endpoints if it's explained to us, our interval is given to us. But we have to figure out if we have any critical numbers on that domain. So I'm going to start, I have the list up here and we're going to just kind of go one by one. So first things first, we're going to find any critical numbers that we have. So I have to take a derivative. I need to set it equal to 0 to find any critical numbers. I notice in this one I can factor out a 12x squared. So then I have 12x squared times x minus 1, which means I have two critical numbers. On that graph, let's check to make sure they are in our interval, which 0 and 1 are both between -1 and 2. So I have two critical numbers, and I have two endpoints, the left endpoint and the right endpoint. So I tend to make a chart. That's my go-to, which basically means that I have 4 options for a high point and 4 options for a low point. So if I'm just reading my chart or my graph left to right, the left endpoint of my interval, which is going to be at x equals -1, is going to be my first potential place for an absolute extrema. Then next comes a critical number of x equals 0. Then we have another critical number of x equals 1. And last we have the right endpoint of x equals 2. Now our critical number is going to happen at any of those places. I'm guaranteed to have a max and I'm guaranteed to have a min, or sorry, our absolute extreme is going to happen at one of those places because I have a closed interval, so I'm guaranteed to have both an absolute max and an absolute min. Now, these two kind of go together in my little chart. I'm going to test to evaluate that number is. I actually need to know what it is on the original graph. I need to know the y value on the original graph at -1, at 0, at 1, at 2. And once I have what those values are, I will know what point then is going to be our absolute max and what point then is going to be our absolute min. So I'm going to just test these in each of my, or going back to this equation. So when I plug in -1, I'm going to get -1 cubed, or to the 4th is positive. So I have 3 minus a -4. So we're going to have y is 7. When I plug in 0, I have 0 minus 0, so I have 0. When I plug in 1, I'm going to have 3 minus 4, which is going to be -1. And when I plug in 2, I'm going to have, well, 2 to the 4th is 16 times 3 is 48, minus 4 times 8 is 32. So I'm going to end up with 16 left over. So what I'm really focusing on, those are the y values. What I'm going to focus on are these 4 values that I just came up with. I'm going to look, well, -1 is the lowest, so that means that we have an absolute minimum at the point 1, -1. And we have an absolute max, let's extend this, at the point 2, 16. So we are actually, in this case, getting a min from a critical number and a max from an endpoint, which can happen. So there's your process of finding absolute extrema. Let's do one more. So we want to start by finding our derivative. Our derivative is 2 minus 3 times 2/3 is going to be 2x to the -1/3. And we want to simplify this. 2 minus 2 over x to the 1/3. And this is exactly the beginning of the reason why we wanted to have everything when we were finding derivatives in one fraction, simplified, factored as much as we could, because essentially of finding critical numbers. So we'd have x to the 1/3 in the denominator. I'm going to multiply by a well-chosen one right here so that I have a single fraction there. The reason why I want that is so that I'm ready to go and find my critical numbers. My critical numbers, when I'm going to have a horizontal tangent, are going to be when my numerator is equal to 0. And I have another critical number down here when my denominator is equal to 0. And I'm not going to get that or notice it if I don't have my fraction combined into one big fraction. So I have two critical numbers. Now I have a little sketch on my page so that I know what this looks like. But if you want to know what this graph looks like, it's that. So here's the horizontal tangent, and this little cusp thing is where we're equal to, or where our derivative doesn't exist. So that's kind of an idea of what the graph looks like. But I have my two critical numbers now. And I need to set up they both happen to fall in my interval, which is -1 to 3. And I'm going to set up my little chart here. I tend to do a chart just because I think it kind of keeps things nice and organized. I have a left endpoint at x equals -1. I have a critical number at x equals 0. And I have a second critical number at x equals I'm at 1. Sorry, not -1, +1. And I have a right endpoint at x equals 3. We're going to plug each of these in our original equation to find out what their y values are. I'm going to help you out right here and just kind of run through what they are. When I plug in -1 into the original equation, I'm going to get -5. When I plug in 0, I'm going to get 0. When I plug in 1, I'm going to get -1. And when I plug in 3, I get roughly -0.24 something. It's actually not going to be anything for us if you look at what we have. We have a low right here at -5, so that's a minimum. So we have an absolute min at -1, -5. And the highest value is that right there at 0. So that decimal actually doesn't mean anything to us once we find out which ones our maxes and mins are. Now, one thing that a lot of students mess up on, keep in mind what these coordinate points mean. The x-coordinate, forgot a parenthesis, the x-coordinate is where it happens, but the y-coordinate is the actual value. So if the question asks you, what's the absolute maximum value, you're not answering the question with an x-coordinate. You're actually answering the question with the y-coordinate. And another thing that kind of sometimes confuses people, and trig is actually the best example of it. If you think about like what your curves look like in trig, all of these points are your absolute maxes, and all of these points down here are your absolute mins. And they happen more than one time, and that is okay. You can have an absolute min or absolute max happen more than once, but it is only one value that it happens at. The y value is that is. But it can happen at multiple x points. So I want you guys to work on the worksheet where we practice finding absolute extrema then.